Hello everyone, I'm Sheikh Urfa from ECEC. My roll number is F6. Today my topic is Introduction to Power Density Spectrum. Power Density Spectrum. Let us consider a random variable x of t. The amplitude of the process varies randomly with time, so it usually does not satisfy the Dirichlet conditions required for applying a Fourier transform directly. Therefore, instead of applying Fourier transform to x of t itself, study the autocorrelation function of Whiteson stationary means WSS random process. The autocorrelation function is used to analyze the specific characteristics like power density spectrum and power spectral density. Both are same. Definition for power density spectrum. Power density spectrum of a Whiteson stationary random wave process x of t is defined as the Fourier transform of its autocorrelation Rx of tau. It is given as Sx of omega is equals to integral minus infinity to infinity Rx of tau e power minus j omega tau data. The inverse relationship is true. The autocorrelation function can be obtained from the PSD using the inverse Fourier transform. Rx of tau is equals to 1 by 2 pi integral minus infinity to infinity x of omega e power j omega tau beta. Thus, the power spectral density and autocorrelation function are Fourier transform pairs. The purpose of using power density spectrum tells us the power of the random process is distributed across different frequencies. Why we use autocorrelation? Since a random process may not have a simple Fourier transform because it's random. We study its autocorrelation instead, which is smoother and well-defined. Fourier pair relation. The autocorrelation function describes how signal values relate over time delays, example time domain and frequency domain, while the PSD shows how signal power spreads over frequencies. In these we use frequency domain. These two are connected by Fourier transform. The physical meaning of this is PSD shows which frequencies contain most of the power. For example, if a random signal's PSD is high at low frequencies, means the signal varies slowly with time. The Whiteson stationary process x of t. The average power represents the mean energy of the process per unit time. It is defined as the time average of the second moment or expected value x square of t. Mathematically, it is represented as Txx equals to limit t tends to infinity 1 by 2t integral minus t to t p of x square of t dt. This is the power formula. For WSS random process, the expected value t of x square of t is equal to the autocorrelation function at zero lag. That is, Txx of is equals to Rxx of 0 means power is equals to correlation of 0. Relation with power density spectrum. We know from the power density spectrum that Rxx of tau is equals to 1 by 2 pi integral minus infinity to infinity xxx of omega e power j omega tau d2. If we substitute tau equals to 0, then Rxx of 0 is equals to 1 by 2 pi integral minus infinity to infinity xx of omega d omega. Hence, the average power of a random process is power is equals to 1 by 2 pi integral minus infinity to infinity x sxx of omega d omega. This equation shows the total average power of a WSS random process is equals to the power spectral density curve. Now we see the properties of power density spectrum. The first property is Sxx of omega greater than or equals to 0. Now the proof is from the definition the expected value of a non-negative function e, of modulus of x of t omega square is always non-negative. Hence, we can say that xx of omega greater than or equals to 0. The second property is the power spectral density at zero frequency is equals to the area under the curve of the autocorrelation Rxx of tau. That is, Sxx of 0 is equals to minus infinity to infinity Rxx of tau d tau. The proof: from the definition we know that Xx of omega is equals to minus infinity to infinity of tau e power minus j omega tau d tau. For a, if we substitute omega equals to 0, Sxx of omega is equals to minus infinity to infinity Rx of tau d tau. The next property is the power density spectrum of real process x of t is an even function, that is Sxx of minus omega is equals to Sxx of omega. X of t is real. Proof: consider a WSS real process x of t, then we can derive it as the following process. We can derive this expression. Since x of t is real, from the properties of autocorrelation of equation, we can say that x of x of minus omega is equals to x of omega. The fourth property is Sxx of omega is always a real function. The proof: from equation 7.3 we know that xx of minus omega is equals to limit t tends to infinity e of x of t of omega whole square by 2t. Since the function x of t of omega whole square is a real function, Sx of omega is always real. And this is the fifth property. If Sxx of omega is a PSD of Poisson stationary random process x of t, then 1 by 2 pi of minus infinity to infinity xx of omega d omega is equals to a of x square of t is equals to Rxx of 0, or the time average of mean square value of Poisson stationary random process equals to the area under the curve of the power spectral density. And this is bandwidth of the power density spectrum. Baseband process. Assume that x of t is a pass low pass process, that is, its spectral components are clustered at origin. Omega is equals to 0. As frequency increases, the spectrum magnitude decreases. It is inversely proportional. As we shown in the figure 7.1, the normalization of a power spectrum is a measure of its spread. It is called RMS bandwidth. The RMS bandwidth is obtained from W square RMS is equals to minus infinity to infinity omega square Sxx of omega d omega by minus infinity to infinity xx of omega d omega. Band pass process. In a band pass process, the spectral components are clustered near some frequencies, omega naught square and minus omega naught square, as shown in the 7.2. The mean frequency omega naught complement can be expressed as omega naught complement. Here is the formula as shown in the figure, and the RMS bandwidth is, we can write omega square instead of omega minus omega. Then the RMS bandwidth can be represented. The power density spectrum of a baseband random process x of t is Sxx of omega is equals to 2 by 1 plus omega by 2 whole square of whole square. Find the RMS bandwidth. We can find the RMS bandwidth by using this formula, and we can get the answer as 8 pi. We can do the W square of RMS is equals to 4. Then W of RMS is equals to 2 radical per second. The advantages of PSDs. Frequency insight shows how signal process is distributed across frequencies. Second, noise identification helps detect and analyze unwanted noise. System diagnosis useful for finding faults, vibrations, or irregularities. Efficient analysis converts complex time domain signals into simpler frequency domain forms. Broad applicability used in communication, biomedical, mechanical, and many other fields. The disadvantages of PSDs: loss of time information, frequency analysis ignores when events occur, assumes stationarity, works best for signals whose properties don't change over time. The resolution trade-off limited by window size, computational cost, requires more processing than simple time domain analysis. Interpretation complexity can be harder to predict for non-periodic or noisy signals. And finally, we can see the applications of PSTs. Signal processing. Analyze frequency content of signals. Noise analysis. Identify and measure noise levels at different frequencies. Filter design. Create filters to remove unwanted frequencies. Communication systems. Steady bandwidth and inference. Audio or speech processing. Detect tone and noise. Vibration analysis. Monitor machinery or structural vibrations. Seismology. Analyze earthquake frequency content. Biomedical signals. Study EEG, ECG, or EMG frequency patterns. Astronomy. Analyze variability in light or radio signals. Radar or sonar signal systems. Characterize signal returns to structure. And thank you.